special lecture will be given by Felix Kubler. Felix is very well known for his work on general equilibrium, both theoretical and computational, bringing these two areas closer together through his work on during the past 15 or 17 years. Felix got his PhD from Yale University and had positions at Stanford University, Mannheim, University of Pennsylvania, and now University of Zurich and the Swiss Finance Institute. It's a pleasure to have you here.
Thanks.
It's all yours.
Thanks a lot, Mario. I would like to thank the organizers for putting together this great conference at a wonderful location, and then for inviting me, which was extremely nice. And I'm a little bit in trouble though, because after a whole day of excellent talks, it's clear that I'm not going to keep up with it. So I decided not to try. Okay, so I'm going to I'm going to spend relatively little time trying to explain what we do in the paper, and I'm going to spend a lot of time motivating the exercise. So I'm going to spend a lot of time sort of reviewing work I and others have done on the problem, motivating the problem, and then I'll try to explain the basic idea of the paper without too many equations. That's probably not going to work so well, but still I'm going to try. Okay, so I'm happy to give this talk in honor of Aloisio, and as I said, I'm going to spend a lot of time on the problem of computing equilibria in stochastic models with overlapping generations and with collateral constraints. So the motivation of this line of research is that 20, 30 years ago, people understood that the classic general equilibrium model had this problem that everybody always keeps his promises. So all deliveries are made and so on and so forth. So there's no room for default, no room for people not doing what they're supposed to do. And then many researchers, including Aloisio and many others, started writing down models which allow for default. And these class of models, I don't think we have converged to one canonical model, but one model which is very tractable and very easy to sort of handle, very easy to understand, is a model where the only reason not to default is because you put up some collateral, you put up some durable good or some physical asset as collateral for your promise. Okay, and this model so was probably first written down by Janelis and Zame in 2002, and obviously it abstracts from a whole lot of important things. Okay, it abstracts from reputation, it abstracts from the fact that there's substantial amounts of unsecured debt in the economy, but it turns out still to be a useful model to sort of try to work with. Okay, and within this model, probably most famously, Janelis works out a three-period example of what he calls a leverage cycle. So he wants to push this idea that in boom times, people take on too much leverage, so they put too much debt on their collateral, and then in busts, everything goes south, and bad things happen. Okay, so actually, Araujo, Susan, and I have a paper where we also sort of examine the role of collateral and borrowing, and we sort of show that what's crucial is the distribution of possible collateral, so the distribution of durable goods among households, and how much of it there is in the economy. So that's going to play an important role for the well-functioning of financial markets. And in all these stories, though, you sort of wonder how to go beyond 2 or 3 periods, right? So if you talk about the leverage cycle, it's sort of hard to think of cycles just existing in 3-period models. If you talk about the distribution of collateral among agents in the economy, obviously it's going to evolve over time, and you want to understand a little bit how it's going to evolve over time. And it turns out that Aloisio also there was one of the first who wrote down a consistent infinite horizon model with infinitely lived agents with collateral. So in this paper with Pasqua and Torres Martinez, they write a very nice model and actually show that collateral constraints help to get existence, right? Because they rule out Ponzi schemes. So they actually do something good. They actually make the model more tractable. And Carl Schroeders and I, we sort of worked out a computationally tractable version of this. And you can solve for equilibria in these kinds of models with collateral constraints. Now it turns out that it's very difficult in a stationary infinite horizon model with infinitely lived agents to get the sort of effects you want. So it's very difficult to get leverage cycles. It's very difficult to get large bust and booms episodes. And one of the reasons why it's difficult is because people, they save. So collateral constraints eventually are hard it's very hard to get them binding. Okay, so attempts in the literature, they find very small effects. So I'm a co-author on this paper, so I can say that, we tweak the model, we twist the model, we work extremely hard to get anything, and at the end, the effects are very small. And, Caro uses heterogeneous beliefs to get more effects, but even then, it's a little bit hard to see what's going on. Now, the situation is obviously different in overlapping generations when some agents are born into the economy and they have no collateral. And I want to argue that, this idea that the young might not have collateral and are borrowing constraints might play an important role. So it's a little bit embarrassing to have some data here, but this is sort of supposed to be some data which nobody can read because I'm afraid that even I have difficult readings here. But, so this is a percentage of consumers without debt, and it goes down until people are like 67 or something, and it's very high for the young. These are mortgages, so clearly the young have very little mortgages. Now, there are two reasons for that. One is they might not want a big house, right? So if you're 20, you don't need a 5-bedroom house. But I think another reason is that they are simply borrowing constraints. And this mortgage debt is substantial. So the median debt is $160,000 in the US, and it sort of peaks at the age of 40. Okay, and then home equity lines of credit are also substantial. It sort of peaks at 50 to 57. Okay, so, as I said, it's not clear whether it's taste, that these people just don't want houses, that's why they don't have mortgages, or whether they're borrowing constraints. So there's obviously a literature on this in macro, and my reading is that it's a combination, but it's also pretty clear that, there are a lot of young people who are borrowing constraints, who cannot buy houses and who don't have collateral, they don't have really access to borrowing markets simply because they haven't accumulated any wealth. And so the sort of effects you see in both the leverage cycle and in the work I did with Aloisio, I think, could play an important role in these models with overlapping generations. Now, the bad news is we then need to find a way to find equilibrium in these kinds of models. Okay? And the main part of my introduction here to the paper I actually want to present is that this is very hard. Okay, this is incredibly difficult. So why is this difficult? Well, because you need to solve for recursive equilibrium. But what's the state? The state is the wealth distribution among agents. Now, if people live for, say, 60 periods, say a period is a year, so you have a 60-dimensional wealth distribution, only if you have one guy per generation. If you have heterogeneity in generation, the wealth distribution is like 120-dimensional, 180-dimensional. So it's very hard to solve, there's a curse of dimensionality because you have to approximate the policy function and the pricing functions as functions of 100-dimensional state space. That's tough to do. There's also an issue about existence. So for theorists, it might not be the best way to go. Now there's an alternative which was pioneered by José and Smith, Chien and Lustig, Cole, Chien and Lustig, and it's a little bit ad hoc. So I'm going to come back to what they're doing, but if you want to, so I'm going to, in a minute, start talking about bounded rationality, which one might not like so much. If you want to, it's like a theoretical foundation of what these people do, and you can just view it as a method to find equilibria in stochastic overlapping generation models. Okay, so the computation is hard. So if agents live for 60 periods, and even there's one guy per generation, you have the 60-dimensional state space. There have been papers who attempted to solve it. So there's a paper by Hazan Hodge and Kotlikov who have 80 generations, but their approximation is very poor. Then there's a paper by Brum, Scheidegger, and me, which I want to spend, do a little detour, spend 5 minutes on what we're doing there before moving to, what I want to actually present. So the reason why I do this is sort of I want to try to show that I tried hard, okay? I tried hard to solve this model with the right methods, and I couldn't do it, so that's now motivates me to write down a different version of the model. Okay, so here's what we did. So Brum and Scheidegger in an earlier paper, they read a bunch of math books, and Scheidegger is a physicist, so he knows a lot of stuff about high-performance computing. So they found this way, which is called the sparse grid. So it's a very good methods to approximate high-dimensional functions, and they combine it with high-performance computing. So they have access to a supercomputer. And we tried that on an OLG model, so I just want to tell you how this method works on the kind of models I want to solve, on models with overlapping generations and collateral constraints. So the basic idea is, so if you want to approximate a function of high dimensions, the easiest way to do it is to take tensor products. But that means that you have trillions of points, even in 20 dimensions. And so in the 60s, this Russian guy, Smolyak, came up with an idea, which was to say that if you assume that the functions you want to approximate have bounded mixed derivatives, you can throw away a whole lot of these points. So you need much fewer points, it turns out. And so this, what's called Smolyak's method, has been applied to economics relatively successfully. But it turns out that, I can say this because with Krüger, we were the first to find it. We found it in an old math book, and we just, didn't read more up-to-date math papers. So this guy, Griebel, in the beginning of 2000, has sort of, took it to a new level by using different basis functions. And so that's what we do. We use this idea from Bunkertz and Griebel, and we use what's called adaptive sparse grids. So not only you throw away a whole bunch of points, but then you also have constructive methods to introduce new points, to put points where you need them in the state space to get your function approximation going well. Okay, so Pflüger wrote his PhD dissertation on this, and this is actually his algorithm which we're using. So just adaptively refines the grid. And then we use, it's a little pompous to say this, but it's true. So, in Switzerland, they have a lot of money. So they have these supercomputers, and they let economists use them. In the US, they have faster computers, but they only use them for developing nuclear bombs and stuff like that. Also in China. But, the Swiss, they let economists use them by saying, we figure something good out for the economy. So peta means 10 to the 15. So these are very fast, but you need to find a way to effectively code. And it turns out that, value function iteration or policy function iteration is fantastic for this kind of architecture. So, the computer science people, they cannot believe our results, our scaling results, because their problems are of different nature. So they don't do value function iteration. So if you do value function iteration, or, in the OLG, it's a little bit more involved because it's not actually a value function. You have the policy next period, and then you find the optimal policies this period, so optimal prices and choices of agents so that the first order conditions hold. You have thousands of points here, but you can distribute the points to different MPI processes. And within each MPI processes, so a node here has 8 CPUs, and then you use TBB so some Intel language to distribute them in the nodes. And then these modern supercomputers have a GPU, graphical processing unit, attached to each CPU. So that you use for the interpolation, right? So if you need to interpolate the policy and pricing function in the next period. And so this works fantastically, as if these computers were designed to do dynamic programming, which they're not. So, so that's what we do. And we can solve 60 periods, so we can solve the model with one agent, but without collateral constraints. So just a risky asset. And what you see is to get reasonable accuracy, so around 10 to the minus 3 here, you need 20,000 points. So at each point, you have to solve a system of 60 nonlinear equations. So it's very costly. So even with supercomputers, you cannot go much beyond that. Okay, that's just what it is. So, and then comes the problem with collateral constraints. So collateral constraints only make sense when they're occasionally binding. So once in a while they're binding, once in a while they're not binding. So there are regions of the state space where they're binding, regions where they're not binding. In between, there's a kink. So the policy functions and the pricing functions, they're not going to be smooth functions. So, suppose a function looks like this. This is a standard test function, 2 dimensions. So the sparse grids works well for this, because the sparse grids put a lot of points here. So these are the points endogenously chosen by the algorithm. They put a lot of points in the kinks and very few points where the function is smooth. But you still need a lot of points in 2 dimensions. So in 60 dimensions, there's no way to do it. So here, so these are normal sparse grids. You get no accuracy. You need 10 to the 6 points to do anything. Here we need 4,411 points for accuracy of 10 to the minus 2. but it's in 2 dimensions. So, just try to convince you that I tried really hard to do it right, and I couldn't. So what's the alternative? So the alternative is to do what Per Cosell and Tony Smith, did a long time ago. So they sort of, they don't call it that, but it's sort of self-confirming equilibria they compute. So agents have very simple forecasting functions. So they use, in their model, it's just the neoclassical growth model with heterogeneous agents. They use aggregate capital to forecast the future evolution of prices, which is obviously incorrect because the vast distribution matters. But with that you can solve it, and then you can solve for the optimal forecasting rule. And in many models it turns out to work extremely well. In some models we now know it turns out to work extremely badly. So Cosell-Smith write, the calculated option satisfies all the standard equilibrium conditions except the agent's ability to make perfect forecasts. But then at the end, the accuracy is so high that we find it very hard to argue on the basis of irrationality of the agent in our model that our approximate equilibrium is a less satisfactory economic model than exact equilibrium. Okay, so this method works well often. It's a little hard to judge what works well and what works not well, right? So this is obviously a huge judgment call by these guys. The accuracy is so high. So I want to take the idea and make it explicit. And by doing so, we're also going to allow for some people to make bad forecasts. Okay, so we're going to allow for heterogeneity. Maybe there are some guys who are not so good in forecasting future prices. And we would have to see what happens to them. They get very poor or they do okay. So we'll see. Okay, so that was the introduction. So now going to give you a few equations with a model, and then describe what we're doing with bounded rational agents. If you don't like bounded rationality, just forget it. Just call it, whatever. Agents who make small mistakes. It's not, the word is very heavily used. I thought we use it, but if you don't like it, it's fine. So we show existence and we talk about computation. This is going to be the main point because computation really works well. Okay, so here's the model. So time is discrete. There's an aggregate shock that follows a Markov chain, finite support. Each period, H types, H could be 1, but could be higher, of ex ante identical agents enter the economy. They live for A periods. They consume a single good and trade in the asset markets. There's no production here, so I don't know how to do it with production. I mean, I understand that Cosell and Smith did it with production, so I can just do what they did. But yeah, I wish I knew how to do it with production. Okay, so the aggregate shocks follow this Markov chain with transition pi. Then we allow for idiosyncratic shocks. So this is this Bewley style idea that agents have, like, you can break your leg, or you can lose your job, and that only affects you, has no effects on the aggregate. So it's a little bit difficult to construct this, and in this audience I should be careful, but there are possible constructions so that agents have this idiosyncratic transition probability to transit from shock y to shock y prime. And so an agent is identified by his type and his shock history, ya, where A is then the age of the agent. And the fractions also, we assume that the stochastic process is such that the fraction of agents with shock history ya is eta h of ya. Now if you do that, the aggregate variable just depend on zt, so they just depend on the aggregate shock. Okay, so that's the idea of this, that was Bewley's idea. And then agents maximize time separable expected utility. Okay, so the assets. There's a single Lucas tree. I don't know if you're allowed to say that if Lucas is in the audience, but so there's a single tree in unit net supply which drops fruits exogenously, and there are J bonds. So these bonds only. So this is a standard collateral model which Aloisio used and John used, and I'm going to comment on it a little bit. So there are these J bonds. They just differ by their collateral requirement. So the collateral requirement tells you how much of the durable good, in this case, how much of the Lucas tree, do you have to hold in order to borrow 1 unit in this tree, in this asset. We call that Kj. Okay, and we make the strong assumption that if the collateral associated with the loan is smaller than the promise, the guy is just going to hand over the collateral. Okay, so this is a very strong assumption. The payoff of the asset is the minimum of the face value 1 and the value of the collateral associated with that asset. You know, since Aloisio is here, he can defend me if people get angry at this assumption. You know, so obviously the assumption is bad because there are many loans that are recourse. So, you know, the amount of non-recourse loans is not that large. It's not that small, but it's not that large. But even if you would focus on non-recourse loans, it's obviously true that default has implications, right? So, you know, if you foreclose on your house, you're typically not going to move to the next house and do better, okay? So most people who foreclose become homeless, okay? So their furniture is sitting outside, the baby is playing, you know, they have no home. So it's a horrible thing to foreclose for most people, okay? It's not like you walk away from your promise. Your credit score obviously is no good, so you have to climb up your credit score again. There are some social costs, so the value of houses that are foreclosed on typically drops a lot because, you know, these houses deteriorate very fast. It's a moral hazard problem. Okay, so we abstract from all of these pictures, from all of these stories. So why do we do it? Because it's very hard to do it otherwise. So, you know, almost all of you might know this, but you need to keep the problem convex. You know, if you don't have a convex problem, you're done. Okay, so Aloisio now found a way to do it with non-convex problems, but he's cheating. So, you know, you got to keep it convex, and the only way to keep it convex is to cheat otherwise, to, you know, abstract from all these things. Anyway, that's the model. So the intertemporal budget set is, you know, what does your budget depend on? It's your beginning of period portfolio holding, the one you carried over from the last period. It's a payoff of all the bonds, which is determined by the collateral requirements last period. It's current prices, current idiosyncratic shock, and current aggregate shock. And then it's consumption and theta. So theta here is an R plus times Rj. So the first component of theta, which we're going to call theta 0, is a Lucas tree. You're not allowed to short that. And then there are J one-period bonds. So consumption is endowments plus what your previous portfolio of bonds pays, plus what your previous portfolio of the tree pays, minus what you pay for the new portfolio. And then the collateral constraint is simply that the total number of short positions in the J assets multiplied with the collateral requirements has to be covered by the Lucas tree. Okay, so, you know, there are various ways of writing it. I'm writing it like this in units. Most people like it more in margin requirements, but, you know, it's easier for me like this. So then the question is, how is the KJ determined? And the typical way to do it is to say there's a menu of KJ, you know, there's a whole menu of collateral requirements. And in equilibrium, some of them are traded and others are not. And then you have to figure out how the menu looks like. So Susan Schommer did that. I don't know if she's here, but she knows how to do that. And so I'll show you how to do it in a very simple example. Okay, so that's a budget set, that's standard. But now we have to get rid of the problem that, you know, that we cannot find the recursive equilibrium. So how do we get rid of the problem? We say, well, these guys are not so super smart. What does it mean to be not so super smart? Well, so these are, you know, these are like stupid things, you know, obviously. To forecast asset prices, you know, you don't, you know, so there's this joke, 7 provided, 13 buts, but 27 ifs. This is the best stock market forecast to clients I've ever read. Now, this is what we would think in our model, right? So these provided buts, ifs, these are the states of the world, right? And so a stock market forecast would be to say, you know, you list all the states of the world, and then you know the stock price is contingent on the state happening next period. That would be exactly the forecast in our model. But, you know, it's a joke, so people laugh about that. They don't think that's how forecasts work, okay? So they look at past prices, and then they do something. You know, obviously also people make, you know, even given the forecasts, people make mistakes. So some of our colleagues, Bernheim and Kotlikoff, you know, they have the software, which is the financial planning tool. So it helps you compute, you know, your value function, because most people are not able to do it. So, you know, this is obviously, you know, true, has many problems to do it, but let's just do it. Okay, so the Bellman equation is going to look like this. So what's the state? The state is the current prices. So clearly people can use current prices to forecast future prices. And it's a history of shocks. So this z tau, tau is some integer. Z tau is the length of lagged shocks. So you take the current shock, the current economic conditions, but you also ask yourself, you know, what was unemployment last quarter to forecast stock prices tomorrow. Okay, so this is the aggregate state. F has to be in there because it's the payoff of the one-period assets, and theta minus is the individual state. So the value function at HA is simply to maximize your utility given the value function of HA plus 1. But then you have the subjective, this subjective probability kernel, that you have some probability over prices tomorrow, conditional on prices and states today. Okay, and that can be arbitrarily complicated. Now, for the purposes of the rest of today's talk, I want to assume that it works like in a rational expectation model. So people know the possible shocks, they know the probability distributions of the possible shocks, but they don't know which price is realized contingent on the shock. So in other words, it's saying there's some forecasting function Q which tells you, given the shock history tomorrow is z tau prime, so it's z tau plus the aggregate shock that realizes next period, today's price is Q, what's the price in that state z prime tomorrow, okay? And for simplicity, we assume that the probability distributions are objective, so that they make no mistakes knowing the probabilities of the states. They could, but doesn't matter for what we do. We also assume that they can identify the states perfectly. Also, doesn't really matter so much for what we do, but this is the simplest form. Okay, and then then we just solve for temporary equilibrium. So some people who read my abstract said I'm going back to the 70s and it's not so good, but you'll see it's not so bad either. So it looks a little bit bad now, but it'll be okay. So given your forecasts, temporary equilibrium is just that each agent today maximizes his utility function that gives you a demand for assets today, and prices are such that markets clear. Okay. Now, with arbitrary forecasting functions Q for prices tomorrow, you can get everything here. Now, there's collateral plays a role here. It's a paper I didn't put on the slide, but collateral plays a role here, people have pointed out, because with this my form of collateral constraints, your beliefs can be completely idiotic. You're still going to be not starving tomorrow, right? Because you can always default. So if you have the really idiotic beliefs about prices, you're still going to wake up and you're just going to default. But we don't want them to have idiotic beliefs about prices. So we want to put restrictions on beliefs. So that's what we're doing. So what are the restrictions? So the primitives are, these guys have a set of forecasting functions. And let's assume they're polynomials. It doesn't matter. It could be piecewise linear function. It could be splines. Some nice class of functions. Let's just suppose these are polynomials of some degree delta. Then each type H has some cognitive ability, whatever you want to call it, which consists of the degree of polynomials he has as forecasts and how many lags he considers, how many lagged shocks he considers for his forecasts. Okay, and then he chooses a forecasting function to minimize mean squared error over the ergodic distribution. Now, there's existence here because it's not clear that this object exists, and it's not clear that a temporary equilibrium exists where the forecasting function is like this. This is a hard problem, and I wish I had solved it, but neither me nor my co-author, who's my student, and who is smarter than me, so he couldn't do it. So. Also, it doesn't help for computation. So, remember my main motivation was I want to find these equilibria, I want to solve them. So, so we're doing something not so great, but as I said, it's not clear how to do it differently to us, which is we have some epsilon. So agent also make epsilon mistakes in choices, and they made epsilon mistakes in choosing their forecast. So their true forecasting function doesn't minimize this, but it's within epsilon of the minimum, okay? And epsilon, so it's going to be another parameter. So agents' cognitive ability is the degree of polynomials they use for their forecasting functions, the number of lags, and this epsilon. And obviously you want this epsilon to be small. Now, you will see, so, I'm putting my cards on the table here, and, before you think, so this epsilon will be determined by market clearing. So it's a little bit, in the beginning I thought it was very bad, but if you think about general equilibrium, it happens once in a while. So so constant returns to scale, profit maximization is the same thing. Yeah? The firms who maximize profits, they don't know how much to produce. It's determined by market clearing. So here it's the same thing. These epsilon mistakes of agents are going to be determined by market clearing. It's not great, but it's the only way I know how to prove existence. That's not a justification, but it's true. And it's going to make computations incredibly easy. Okay, so that I think is a good justification. Okay, so under standard assumptions, this is epsilon, you can prove existence of what I call here boundedly rational temporary equilibrium. So it's a temporary equilibrium where agents choose almost optimal forecasting functions within the class of their forecasting functions, according to some mean squared error, but it could be some other statistical criterion. And they maximize their utility within some hopefully small epsilon. Okay, and this exists under standard assumptions, so you need to assume a little bit more than strict concavity. You need to assume differentially strict concavity, interior endowment, so more or less standard assumptions. And the intuition is one way to prove it, so I'm not, I'm certainly not going to give you the proof. You're all waiting for Luiso's talk, and as I said, it was a day full of fantastic talks, so I'm not going to give the proof, but the intuition is that, we make a bunch of assumptions which ensure that for each truncated economy, so there's an ex ante known compact set, and for each truncated economy, price line is compact set. So at some point, you can just discretize. So it's a compact set. So you can, for any epsilon, you can find points such that they cover, the epsilon neighborhoods cover the set, and that gives you your prices. So in fact, the equilibrium we find has finitely many possible prices, and that's the trick to computations. So the computation is going to solve for these prices that clear markets with some error, or that approximately clear markets which can be translated to errors agents make. Okay, so what are the properties? So this is the good news now. So for any epsilon greater than 0, for any mistakes people make in their choices, you can find a boundedly rational equilibrium where agents forecast prices correctly. So their forecasts are exact, their forecasts are correct, but they make errors in choices that are smaller than epsilon. Okay, so it's true for any epsilon. As epsilon goes to 0, these equilibria converge to rational expectations equilibria. But of course, in the limit, they are no longer that simple equilibria. In the limit, there's nothing good about this equilibria. Okay, so this is what I meant when you can interpret it as Cosell and Smith. So that's my view of what they did, which is to say, it's not, obviously people make some choices, but here you can prove that, you can make the mistakes people make arbitrarily small if you allow for enough prices in your set. Okay, so now, why did I do all of this? I do all of this because, and this is, if you know this Cosell-Smith, Chen, Colin, Lustig stuff, this is perhaps not so super surprising, but, I think it is a little bit, my method is a little bit better than theirs, as I will explain, because it makes computation extremely simple. So, how does it make computation extremely simple? So, let me try to, I drank some water just to be able to focus for the final stretch, okay? So it happens to me all the time in talks that I start very well, and then at the end, and nobody understands anything. So let me try, if you're lost now, maybe we'll be able to recover here, okay? So here's what we're doing. So we're thinking that there's some large number n or nz that we say these are possible equilibrium prices. Okay, so just saying, you discretize the prices. Now, of course, if n is 10 billion, it's not a good method. But it turns out that n can be pretty small, as I'll show you. So then you can reduce the computation of equilibria to a finite dimensional optimization problem, which is to say you find the correct prices, the n prices, and you find the transition function mapping price today to price tomorrow, such that you minimize aggregate excess demand. So this can be done with standard global solvers. It's not a convex problem, obviously. So it's not, it's not perfect, but there are derivative-free solvers now which work pretty well. So so that's what we do. So so let's just assume in order for me to be able to explain this, that agents have identical forecasting abilities, and they only use the current shock. Okay, so it will turn out that this is enough to get within epsilon to a rational expectations equilibrium if you have enough prices, and it makes explanations very simple. Okay, so suppose these sets boldface Q are the set of possible equilibrium asset prices for each shocks 1 to capital Z. So each of them contains n prices. Now obviously there are finitely many possible functions which map the price into shock today to the price tomorrow, because there are finitely many prices. But there are many, so this actually is a difficult problem, and we have a little bit of an ad hoc solution to it. So suppose, for the sake of simplicity here, that you can compute optimal choices exactly. So you do value function iteration. Given the forecasting rule, it's just value function iteration, right? So the forecasting rule is each agent has this rule. Today the price is 5 and the shock is 1, so tomorrow the price is 7. So you can solve value function iteration, dynamic programming. And let's suppose you can do that exactly. Now, of course, there's some computational error here. You cannot do it exactly. But they're pretty good theories. So, Santos and co-authors have figured out pretty good ways to bound the errors here. Okay, so let's suppose they're 0. So suppose, given the forecasting rule, given some initial state zeta 1 and some initial price Q, any history of aggregate shock Z up to A, so remember A is the lifespan of agents, you can compute individual optimal consumption for each individual, for each H and YA. Okay? Then it turns out that to check the error in market clearing at all possible nodes after A periods gives you the error in market clearing on all the infinitely many nodes of the tree. Okay, so this is the only reason I decided to write this paper, because this is such a simplification that it's worthwhile to sort of use it somewhere. So again, what's the simplification? Simplification is, you define this error criterion over all possible initial shocks. So Z1 is the shock in the first period. Q of Z1 in the set of possible prices is the price in the first period. And then you look at all histories of shocks after A periods. So obviously these are, this max has to be approximated somehow. This is not going to be computationally feasible, just theoretically. You look at all of these shocks, and you look at the error in market clearing here. Okay? If this is below some epsilon, then error in market clearing is below epsilon at all nodes of the infinite tree. Why is that? Well, because here you go through all initial conditions. So here you go through all initial conditions. Everything that can possibly happen after A periods is everything that can happen after A plus 1 periods, because it just shifts the initial condition by 1 period, and you go over all initial conditions. Okay, so this error, if you get this small, you found your boundedly rational temporary equilibrium. So the optimization problem to solve is to minimize over all possible transitions, to minimize over all possible prices this error. Okay, and our existence theorem implies that for any epsilon greater than 0, there's some number n such that this is less than epsilon. Okay? So if this is less than epsilon, you can say, okay, this is actually not what agents do. This is agents optimal C. But they do their C a little bit differently to get market clearing exactly. So you can translate this epsilon directly in what agents choose in markets with market clearing, and then they make small mistakes. That's, that's in some sense the main theoretical result. Then the question arises how to compute these things. Okay, so clearly here you take the max. So suppose you have only 2 aggregate shocks, but people live for 60 periods. These are 2 to the 60 possible histories. So you cannot do that very well. And then how do you solve this minimization problem? Okay, so the way we did it, and it's actually not the ideal way of doing it. So we use this what's called hopspec. So that's a simple line search thing. The advantage is it can be parallelized very easily. But it turns out that there are evolutionary algorithms which are much better. So there's EMS V7, it's called, by some guy who used to be in Zurich, but now, which is much better. But anyway, so this is what we use for the examples I show you. And we solve for the optimal policy for the optimal transition functions using the trial and error method. So what we do is we say, suppose agents don't take the price into account. They just take leg shocks to forecast. That's that turns out that's what the Chen, Call, and Lustig do. And then that implies something on the prices, on the forecasting, on the transition function for prices. We take that as given, and then we look at we randomize our possible one-step deviations to see if we can do better. And we often can do better. Now, note that we don't have to solve this problem, so we don't have to find the minimum. We just have to find something that is smaller than epsilon, right? So we're not interested in the minimum, we're just interested in something that's smaller than epsilon. So we don't care if we found the global minimum, we just care if we found something that's good. So that's what we do. So agent's problem, we solve this policy iteration with cubic splines at approximating functions. So the error there is about 10 to the minus 5. We think that's 0, not quite, but close. And then sort of the main problem is this object, right? So this is no good. This you cannot really approximate. So instead of taking the inf norm, we actually take the 2 norm. So we take the 2 norm, and then it's just an integral. And the integral can be solved very, very well with Monte Carlo. Now, how well the optimizing result under the 2 norm compares to the inf norm, we can just sort of try different examples, and it looks fine, but we don't have a theory of it. Okay, so here's an example. So suppose agents live for 60 periods. Suppose there are 2 idiosyncratic shocks and 2 aggregate shocks. Okay, so there's obviously no way to do this with standard recursive methods, because these 2 idiosyncratic shocks mean that after 60 periods you have 2 to the 60 different guys. So the number of agents is very, very large. There's a tree, and since there are only two shocks, it suffices to look at a single bond, right? So so what are the relevant collateral requirements from here? One is that the bond pays 1, the other one that the bond pays 1 and then less than 1, which is the value of the tree. But that one must be collinear to 1, 1 and the value of the tree. So it's actually enough to look at 1 tree and 1 bond here. And then we assume something about how endowments go over the life cycle and how these idiosyncratic Y influences the shock. So it's relatively standard, we don't assume much. And it turns out that n equals 16 suffices for epsilon to be 10 to the minus 3. So 16 means that for each of the aggregate shocks we have 16 possible prices. So it's 32 prices. It's a relatively small minimization problem. Now, 10 to the minus 3, what does that mean? There you can be of different opinion. Now, it's sort of the same order of magnitude of what Cosell and Smith get, and they call it very small. You can think of it that out of $1,000, these people make mistakes, make $1 mistakes. It's not ideal, but that's what we get. Okay, so that's it's a labor profile in case somebody's interested. So then it's very simple to extend the model and to say, okay, we don't view this so much as a method to approximate rational expectation equilibria, but we actually view this as as a model where some guys make very bad forecasts and other guys make very good forecasts. Now, the presence of collateral again here is crucial, right? Because the guys who make very bad forecasts, the worst thing that can happen is they completely miscalculate, and they think their house is going to be worth $1 million. Their house is only worth $500,000. They're completely underwater. In our model, it's not a big problem, right? They're completely underwater. They just hand over the collateral. Okay. So, and it's the same idea. So you fix an n, and you conjecture that the equilibrium process has z times n points in its support. Of course, how to find n is always ad hoc. So before n was 16, that's typically that's okay. And then for the fixed transition, you solve the minimization problem, where for each type H, the optimal demand is computed with a different forecasting function, right? So once you have, so you minimize this expression, this error expression. Once you have your n prices, you can compute, you have the transition, you can compute the ergodic distribution, you can compute exactly, actually, not with epsilon error, but you can compute exactly the optimal forecasting function in the class. Okay, and you plug that in. So, so existence guarantees that it will work out, and the errors in forecasting might be very high. Okay, so some people might make horrible forecasts. So then you might think it's not a good model. So you might want to change their forecasting characteristics. Or maybe you hope that if they make horrible forecasts, they don't trade very much because they understand that they're out of the market very soon. If they saved a little bit, they make a horrible forecast, they get wiped out. But that's something that's something you can only see if you can solve the model, and with a sort of two, tricks. Or the main point is to put in the epsilon. That really makes existence and computation very simple, makes the model much more ugly, but for the sake of being able to solve it, I'm sort of willing to do that. Okay, so that's sort of it. So, so the whole point here is to say that there's a large class of models which I find interesting, where you cannot just write down the exact recursive equilibrium and try to approximate the functions, even if you use very fancy methods, and allowing for bounded rational agents. What does it mean here? It means that they make small mistakes. That simplifies the computations tremendously. Okay, so it really gives you a method to solve these models relatively fast. With the example I gave you, you might think was a little dinky. It was a little dinky, but this was done last week, so I didn't. Anyway, so one can solve relatively complex models with this thing. The next seven, that's just a question of whether one finds it interesting or not. I don't take a stand on it. Is to say, perhaps heterogeneity in forecasting abilities is important. Perhaps it plays a role that some guys make huge mistakes in their forecasts. And one, so the stuff I did with Aloisio, which is this model, people often claim that our default is always strategic. So in what sense is it strategic? It's strategic in the sense that that if state 3 happens, the price is going to be 0.5, but you put on so much debt that you're going to default. So you plan it. Now here, if people make mistakes, you can get accidental default. Accidental default in the sense that you really want to keep your house, so you might be able to put in some additional cost of default, and people still default because they really want their house, and they actually didn't plan to default, but then all of a sudden they made a mistake in forecasting the price, and now they're screwed. There's obviously, there's some literature about default and heterogeneous beliefs where equilibrium doesn't exist. So here equilibrium exists always because of these simple collateral constraints. Okay, so that's all. So I have to say happy birthday to Aloisio.